Hey everyone, welcome to our last unit, the unit I'm going to call the beginnings of Las Vegas math. So this is a really different kind of math actually, this last unit. And well, let's jump in and you can see what it's kind of like. Alright, so first lesson we're going to be looking at something called the fundamental counting principle. And for an example of where we would use this would be a situation like this. Joe's shopping for a car. The dealer says he has 3 different models, and each model comes in 5 different colors. So there's something called a tree diagram that you could use to figure out how many choices Joe has. So he could choose model 1, 2, or 3, and then branched off of each one of those, he could choose blue, red, purple, white, or black. So as a result, he would have a total of, if you look at all of these and add them up, a total of 15 choices. So what fundamental counting principle is basically saying, okay, for this choice, which is the model number, so it's really number of choices times the number of choices. For color, this would be for model, and this would be for color. Number of color choices. Okay, so in our case that would mean 3 choices for models times 5 for colors. Oops, I wrote 15 already. Times 5 for colors would equal 15. Okay, now you can do it obviously with more than 2 things that you have choices for. So let's look at example 1. Okay, now they mentioned on example 1 actually showing a tree diagram. Now that can be a bit messy, but basically for part 1 it can be red, white, blue, or pink. So you would have red, white, and you want to kind of spread these out a bit, otherwise your tree is going to be hard to draw. Blue or pink. And then for each one of these colors for part 1 you would then have a different middle part, which could be orange, purple, or black. So from each of these you would have branches coming off, hence the name tree diagram. And each one of these branches is for orange, purple, or black. Orange, purple, or black. And I'm just abbreviating now. Oops. Orange, purple, or black. And then pink for part 1 could also have orange, purple, or black for part 2. Then, finally, the bottom part could be yellow or green. So, off of each of these branches here, you'd have another 2 branches coming off. And that could be yellow or green, yellow or green, yellow or green. So, assuming we were to finish all these, how many would we have at the end here? Well, for each one of these, we would have 2 coming off. And for each one of our initial parts, which is 4 of them, we have 3 coming off. So we should end up with, let's see, we have 2, 4, 6 for red. So we should have 24 altogether. Okay, so 24 choices for different colored toys. Now, using fundamental counting principle, which is way easier, you basically have 3 situations where you have to make a choice. There's the part 1, and then there's part 2, and there's part 3. Part 1, you have 4 choices for color. And part 2, you have 3 choices for color. And then finally part 3, you have 2 choices for color. Multiply them together, and look at that. You get the same number of choices as if you'd done the tree diagram. Okay, so which is easier? Yeah. So it's good to know how to do the tree diagram, but for sure we're going to use fundamental counting principle mostly for this lesson. Okay, let's look at the next page. Okay, so what we discovered there was we found the total number by multiplying our choices together. And that's pretty much the case for this entire unit. If you see the word "and," it basically means multiplying in this type of math. Okay, example number 2, let's put that to work. Math 30 quiz has 8 multiple choice questions. So really, each question has 4 choices. So how many choices would we have to make on this test? Well, there would be 8 situations where we have to make a choice. So I do 8 blanks to represent basically each question where you make a choice. Now in the first question, you would have a choice of A, B, C, or D. So 4 choices. Second question, 4 choices. Third question, 4 choices, etc. Each one of these questions would have 4 choices. So really what that turns into is 4 to the exponent 8 if you multiply 4 by itself 8 times. All right, now we could basically have these same scenarios, but restrictions show up. And what that means is there's going to be some sort of condition that happens on a certain thing that you're making a choice out of. So example number 3, let's look at this one. Eric has been assigned the task of determining how many odd 4-digit numbers there are. He has been told that a number such as 5267 is a 4-digit number, whereas 0267 is classified as a 3-digit number. In other words, what they're saying is 0 cannot be used as the first digit. In other words, we need to make this a 4-digit number, any number but 0 in there. Okay, so first step of his work is shown. We want to begin with our restrictions. Okay, begin with restrictions when you're trying to figure this out. So if it's an odd number, that means the last digit is 1, 3, 5, 7, or 9. So given that, we would have 5 choices. So this is number of choices. All right, so that's basically where that 5 is getting from. Number of choices, you're choosing from 1, 3, 5, 7, or 9 because we need an odd number. Okay, now secondly, he went to the first position, and the reason why is the first digit can't be 0. Okay, if it was 0, we would have a 3-digit number. So we could have 9 other digits, 1 through 9 basically, so not 0. And they didn't mention, yeah, we can repeat digits, so that means whatever digit we used in the last position, we can also use in the first position. Okay, so there we go. Now we're going to complete his work by filling in the last 2. So we have 5 choices for the last digit, 9 for the first, and then after that, we really don't care what it is, right? We've got our odd number, we've got 0 dealt with on the first digit, so we really would have 10 choices for digits. Digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are all our digits, and if you count them up, you'll notice there are 10. Okay, now he's part B here. He's now been assigned the task of determining how many odd 4-digit numbers there are which have no repeating digits. So that means if we use a digit in one position, we can't use it again in another position. So it says, explain why the first step in A is still valid, but the second step is not. And the reason why is when we're looking at the second step, we can't be 0, of course, because it's the first digit, but we also can't use the number that we used in the last position. So as a result, let's do this. We would have 5 choices for odd numbers. Then, in the first position, it can't be 0, but it also can't be the number we used, can't be this number. So we don't know which one it was, but it was one of 1, 3, 5, 7, or 9. So as a result, number of choices drop down to 8. Okay, now for the second position, I have now used up 2 digits. I used up 1 digit in the last position, and I used up 1 digit in the first position. So of the 10 digits, I would only have a choice of 8 remaining. And then finally, in the next position, 7 remaining. And whatever those multiply together will be our answer. I'm not as concerned about multiplying these out. Of course, you're going to want to do that on your questions in the assignment to see if you got the right answer. But for the lesson, we're more concerned about just getting the right numbers in the position. Okay, let's look at the next page. All right, example number 4. Car license plates in an African country consist of a letter other than I or O, followed by 3 digits. So 1 letter followed by 3 digits. Okay, so only 4. Oh, wait. The first of which cannot be 0. Oh, then followed by another 2 letters. So any 2 letters which are not repeated. So in other words, we have 6 positions to fill. Okay, so let's go through this. First one has to be a letter, and it can't be I or O. Can't be I or O. Now there are 26 letters in the alphabet, so if we remove I and O, then we have 24 choices. Okay, times, because it's fundamental counting principle, 3 digits. The first can't be 0, so this one can't be 0. Okay, but other than that, I think we're okay. So that means we have 9 choices, because 10 take away 0. Okay, take away the choice of 0. Okay, and then it said 3 digits. So I guess after that we could probably repeat the numbers. So we would have 10 choices, and then another 10 choices. And then these two have to be 2 letters, which are not repeated. Now, I think we'll assume that just these two can't be repeated, but it can be the same as the first one. I don't know, we'll go with that. So that would mean 26 choices and then 25 choices. And there we go. Whatever that turns out to be, it'd probably be one big whopping number, I tell you. Okay. Example number 5. All right. So we have 2 routes from Pitland, okay, to Queensville. Come on, living in a place called Pitland. Okay, lovely. 3 routes. That must be made up. That can't be real. Okay, 3 routes from Queensville to St. Luke's. Okay, so I think this is Pitland, the P. Queensville is the Q, and St. Luke's is S. Okay, and then 3 routes from Pitland to Rutherford. There we go. Here's our 3 paths. And 1 route from Rutherford to St. Luke's. Okay, so how many routes are there from Pitland here to St. Luke's passing through Queensville? Okay, well, to get to Queensville, we could go this way or this way. So to get here, we would have 2 routes. Now, then to continue on to St. Luke's, we could go this way, or this way. Now, because there were 2 routes to get to here, there'd be 2, and then 4, and then 6. So a total of 6 routes to get to St. Luke's. 2 to get to here, and then from those 2, we could go any of these 3. So 2 plus 2 plus 2. Okay, so the answer should be 6 routes. All right, how many routes are there from Pitland to St. Luke's passing through Rutherford? Okay, so that means this time we need to go this way. So to get from Pitland to Rutherford, we have 1, 2, 3 possibilities, so 3 routes to get to here. And then Rutherford to St. Luke's, there's just the one way, so that would be 3 routes through Rutherford. Okay. Now, how many routes are there from Pitland to St. Luke's? And they didn't specify which one you had to go through. So if we went this way, there'd be 6 routes, or if we went this way, there'd be 3 routes. So 6 plus 3 would equal, that's supposed to be an equal sign, would equal 9 routes. Okay. Now, in general, when we use the word or in this unit, it means we're adding. Okay, another good thing to remember. Okay. Now, example number 6. Telephone numbers allocated to subscribers in a rural area consist of one of the following. The digits 3, 4, 5. Okay. But these have to be 3, 4, and 5. So that would mean just one choice for each of those. Okay. And then followed by any 3 further digits. 1, 2, 3. Or, so that means we're doing another scenario. So we're adding, that's the word or, a digit 2 followed by one of the digits, followed by any 3 further digits. 1, 2, 3. Okay, so we just need to fill in the blanks for a number of choices. Let's look. So digits 3, 4, 5 followed by any 3 further digits. So there's 10 digits, and they said any 3 further, so 10 times 10 times 10. The digit 2, so this has to be a 2, so one choice there, followed by one of the digits 1 to 5. So that would leave us 5 choices for the next position, because that has to be 1 to 5, followed by any 3 further digits. Again, they're not saying which ones, so we would have all 10 as choices. And there we go. Now we need just to work that out, so that's going to be 1,000 plus 5,000. So our answer should be 6,000 telephone numbers. All right, good. Let's look at the next page. Hi, I think what we're going to do, because we only have 30 seconds left in our 15 minutes, is I'm going to continue or finish up this lesson, these last 2 examples, in the next video. But it shouldn't be too long of a video, so we'll see you then.